Start the recording. Yeah, so today the talk is about the text-to-speech, and we have the pleasure to welcome Badreddine to address this topic. So Badreddine, I'll let you the floor, going through your work, and then we will take some Q&A at the end.
Yeah, I will just first share the screen with you. So, I will learn it. You are able to see the screen? Yeah.
Yes.
Yes. Cool. So hello everyone. Thanks for assisting for my first presentation at the data intelligence community about text-to-speech. I would like to thank Mr. Thierry Caminel for his invitation. And the topic of today will be about text-to-speech systems. I want also to thank Gilles Salah, Gérard Bailly, Olivier Perrotin, Jean-Philippe Vine, the Director of Innovation, and Youssef Belmegnay, my supervisor, because they have also contributed to this work. So I want to thank them. So I will start with a brief self-introduction. So I'm Badreddine, a lead data scientist in BS Grenoble at the innovation team. We work mainly on voice bots, chatbot, and voice technologies. We believe that the future of human interaction will be voice, and how we say it always, it's not about what you say, it's about the way how you say it. And we try to work on this component more and more. So this is a small overview of myself. For the topic of today, we're gonna talk about, it will be a part of a series of presentation. Today we are going to see the basis of text-to-speech, different text-to-speech approaches, their advantages and disadvantages, how we generate speech using end-to-end approaches. And in the upcoming weeks, we will talk about the data collection, the speech data collection, the adjustment, segmentation, denoising, in order to use this data for text-to-speech systems. In some other weeks or some other presentation, we will also introduce the expressive speech-to-text, how to adapt the style, the emotional state, the variability, and how to synthesize this style emotion for the user, the particular user. And at the final presentation will be about my recent research and my recent approach, how to control styles using syntactic marks. So I separate the presentation in 4 presentations. Today we're going to see just the introduction to understand the basis of text-to-speech systems. So this is the main slide. The main idea. So the presentation of today will be, first of all, we're going to present an overview of and the use cases, the context of application of text-to-speech system, why end-to-end approaches are better than classical approaches. We will more focus on Tacotron 2, which is a state-of-the-art system, text-to-speech system. We will see how we can use the front end and the back end of these systems to generate speech, contextual speech with context. And as a last point, we will talk about what is next, what are the improvements for better and expressive speech synthesis. So first of all, context and application. So text-to-speech systems can be used in a large set and use cases and application. It can be used in any human, robot, human-machine interaction. In healthcare application also, when we want to interact with the patients, with disabled people, and we try to understand their state of emotion and to generate some dialogues and utterance which are very specialized and relevant for them. In self-driving cars, in video games, when we generate automatic dialogues for automatic generated characters. also in audiobooks, in voice assistants, when we want to have more effective and expressive voice assistants that can express emotion and empathy. All of these are the application of text-to-speech systems, especially the expressive ones. So the project, I'm in this research is a part of the Teradia project. It's a research and development project where we aim to develop a voice bot based on AI and personalize it for the patient, where we can manage his emotional aspect, the mood of the patient, and it's a more bigger project. I'm working especially in the verbal and co-verbal behavior, how we generate it, how we can generate this behavior for the patient. So we aim to develop more expressive and more the emotional component of the voice in this project. So now I'm gonna talk about the classical speech synthesis. In this card is the one of this card. You will always see it in all the speech synthesizer system, like concatenative synthesizer system and parametric synthesizer system. We start by normalizing the text, taking the text that we want to from where we want to generate the waveforms. The concept is very simple. It's like we try to divide. This is the old approaches. We try to divide the speech synthesized in some subdomains. The first subdomain, we're gonna check, test, normalize it, and after we use we try to extract the linguistic features, the grapheme to phoneme mapping, and after predicts the duration and the modeling duration, predict the pitch also and acoustic features, and after we use a vocoder for to transform the spectrogram to waveform. So all of these components should be conducted separately, and we most use DSP, like digital signal processing techniques to handily extract all the features. But now we use more the end-to-end approaches based on deep learning that directly converts the text to a waveform. So end-to-end models do not require intermediate feature extraction. We have one unique pipeline model, so we don't accumulate the errors through this through each component. So we have just one block and all the errors are jointly optimized, and for it gives us a better performance. No error exploding phenomenon. This is the advantages of end-to-end speech text-to-speech systems with the rich conditioning and the text-to-speech problem is the sequence-to-sequence problem. We try to see it as a sequence. We want to map time series sequence to another, which is text, sequence of text, to another time series sequence, which is the waveform or the speech signal. And it's many-to-many mapping. And I'm going to do a little reminder of type of RNN. We have like 3 types of RNN, like recurrent neural network. The one we used for language modeling, it's also many-to-many mapping. For machine translation, we want to translate some sequence to another sequence from one language to another language, from English to German. It's many-to-many. With the variant length, the sequence, they have the input sequence and the output sequence, they don't have the same length. We have also the many-to-one RNN, like we want to put language classification problem, and one-to-many sequence-to-sequence approach, like for image description, it's one-to-many problem. And for text to speech, it's many problem with different lengths. The input and the output, it has different lengths. So here in the left, we have the traditional parametric and concatenative methods for text-to-speech generation that I have already showed. So, and in the right, we have the end-to-end deep learning approach. We see that each building block for the sequence-to-sequence model, like the encoder, attention mechanism, decoder, and the neuron vocoder, was replaced by one component in the traditional text-to-speech generation. We can see it here better. So the encoder extracts the linguistic and the phonetic features from the text. We have the attention mechanism that creates the alignment between the sequence of text and the sequence of spectrogram, or the voice, or the waveform. After we had the decoder and the postnet, which generate the pitch, which is the fundamental frequency, and the acoustic features. And then the spectrogram is conducted to a vocoder at the end. The vocoder, it's one component which is similar between the two approaches, the new approach and the old approach. Here we can use like some vocoder, non-neuronal vocoder like Griffin and Lin, or some neuronal vocoder like WaveNet, WaveRNN, WaveGlow, or DeciNet to generate the waveform from the spectrogram. We're gonna enter more in detail on each component. So the mapping from text to speech, we try to split this mapping using the mapping, first of all, the text to spectrogram, and from the spectrogram to generate the waveform speech directly. So the original encoder-decoder framework, in the original in typical encoder-decoder framework, encoder reads the input sequence, which is typically a sentence, compress it into a vector with a fixed length, which is in red here. And after the decoder, try to predict the output sequence based on just one vector. With the one, we take all the input sequence, we compress it in one vector, and after we took from this one vector, we try to predict all the output sequence. Due to the limited amount of compression of compressed information, the encoder can only store just a limited amount of information in this vector. So this is why we introduced attention mechanism to free the encoder from this summarizing process of the entire input sequence in a fixed context vector. And we try to map input sequence to a series of annotation with the same length as the input sequence. So we will discuss this concept in depth in a bit later, and especially in the attention section. So before, when we start a text-to-speech problem, we should choose, first of all, our alphabet. We choose it, our vocabulary or alphabet or number of characters. We choose it based on the language that we address. So we should define, first of all, the length of our alphabet, how much character we're going to use in our language. It depends if this is English, for example, alphabet. And after we create we define also our max sequence length. It's based on our GPU size. Also, we can treat just to like 100. We used for our example 140 40 length sequence text. So the text in the input cannot exceed 140 character, and we create our batch. In French, we added some characters that are just typically French characters. because we did the two text-to-speech models, one in English and one in French. So in our case, we fixed the max length input at 140 characters. The alphabet size was 70 between letters, digits, and special characters for the English. And we construct our matrix to do the one-hot encoding, to take one sequence, multiply it for this matrix, and we do the zero padding. If we have some sequence that its length inferior to 140 character, we just add the zero padding. This is typical in many sequence-to-sequence models. Typically. So this is the architecture of Tacotron 2 state-of-the-art text-to-speech that we used. We have in blue the encoder, which is 3 convolutional layer, and after a bidirectional LSTM. In gray, we have the attention mechanism. In this model, we use the location-sensitive attention. We're gonna explain why we use this attention. I don't want to enter more in details in this slide. In red, we have the decoder part. This decoder part predicts the mail frames and the stop token. We have 2 elements to predict. In this model, we predict the stop token, which tells if in this sequence we should stop our wave generation or our spectrogram frame generation. And we predict also in each sequence, at each step of time, we predict one frame of spectrogram. So we are going to enter more in details about each component. So, for mathematically speaking, or from a mathematical point of view, we consider we have, like for the text, we have a sequence from which we extract, we have kx is the vocabulary size for our case is 70. The tx is the length of the input sequence, 140. Here I will not use the zero padding for lightening the presentation. So we first compute the encoder vocabulary using convolutional 3 convolutional. Here we multiply by our E is the embedding matrix. We take each character, we multiply it by our embedding matrix that we see here, like it's 140-70 size matrix to get the one-hot encoding. It's the E, the embedding E, and after we use 3 consecutive convolutional filters, F1, F2, and F3. And after we apply ReLU, this is the equation. We use ReLU. We use convolutional layers. It's like just image processing. Convolutional layers are useful to present local correlation between inputs by extracting features map useful for modeling the sequence. For example, here we have 2 words, flour and flower. By using these 3 convolutional layers, despite having the same letters FLO, in order to pronounce them correctly, we take on consideration that there is an U for flower and there is another O for flour. So this convolutional layer gives our model this present and past correlation. This is why we use these 3 convolutional layers. And after, to capture the long-term memory context, we use the 2 bidirectional LSTM. So we use we have this, our sentence is I feel happy, but we have this interrogation punctuation at the end. So it's interrogative sentence. So we should synthesize it. I feel happy, like it's a question. So we should give our model a context of the past, and the future, and just, and the input should be read from left to right and from right to left to have this past and future context. And after we have this HG, which are the summaries of each character. For each character, we have internal representation, which is these 12 HCs for each character. Like for I, we have one internal presentation. Until the last question mark, we have H12 for the question mark, which is its internal representation in the encoder system. We use LSTM, so we have all these gates, the input gates, the forget gates, to forget some, to capture only relevant information from the sequence. All these gates are trained, and after we use this hidden states to calculate the context vector, which is this C. And after now we're gonna see the decoder parts, which are the LSTM and the two LSTM layers, and the prenet and the linear projection component. So by adding a small attention network, which is typically a parallel multilinear feed-forward network, the decoder learns not only to predict outputs once a time, but also learn to align outputs with the correspondence input. By learning the attention, the model is no longer forced to decode sequences using a small compressed fixed length true vector, as a traditional approach is very ineffective for a long sequence. So we calculate this soft alignment between decoder output and encoder output. With soft alignments comes soft marks that we use in the computational of attentional weights. So as you see here, we have the context, and we have the decoder. We have the LSTM decoder. His input is E0. In green, I showed the synthesized mode. When we synthesize one MEL spectrogram and one stop token, we take these two and we inject them to the prenet, and we combine the output of the prenet, which is PYY, with the context, the previous context, to calculate each decoder output S0, S1, S2, S3, and after we put them to a linear projection to have to make them looks like a wave, a MEL spectrogram MEL form. So this is the question. So last but not least, once the decoder is done decoding, the predicted MEL spectrogram is passed through a stack of convolutional layers with the tangent to improve the overall output quality. This is the probability due to ability to convolutional layers to capture features in image of sequence, especially that they see both past and future context in already decoded spectrograms. So as to have a recap on all these elements, so we use our encoder, which is 3 convolutional layers, and after 2 bidirectional LSTM, and to get our 512 character embedding. And after we use a decoder. In the decoder, we have also two LSTMs. We map all with the attention layer, and after we process to a postnet to get the MEL spectrogram frame and the stop token. We use also regularization because it's a more complex model, and we try to regularize the learning. So this is all the loss functions of the model. So in the, we have like this model, the tachotron model that we have trained, have over 20 million parameters. The alignment is the relationship between the encoder and the decoder. The encoder is the text, like how I'm feeling, and the decoder is the MEL spectrogram that we have here above. We have the ground through MEL spectrogram and the predicted spectrogram. And for each time step, we try to predict the stop token. We say if we stop here or we not stop, we continue our decoding steps until we finish. So this is the visualization of this linking between the encoder and the decoder. So so tachotron, basically what we learn. We learn we focus more in learning these character embeddings. The character embeddings are very important because at the start we have just one hot encoding. We have like different characters that are the same. All the difference between the characters, each character are the same. So we have no notion of two vectors that are close or not close. So by training tachotron, we get these embedding characters, and we have we extract these features that in traditional approaches we were extracting them manually. Like if these characters are vowel or consonant, that are voiced or not voiced, what are their frequency, their fundamental frequency, F1, F2. But using tachotron and using the convolutional layer and the bidirectional LSTM, we can we were able to extract all these features just directly from our training data. So we're gonna see, like here we have an example. Normally E and Z are two different characters, and they should not have the same representation. So the embedding that was learned automatically takes into account that this one is a vowel and the other is a consonant. One has more probability to be at the beginning of the sentence. The other one no. So all of this is computed in 512 vectors. And after when we have our embedding matrix, we multiply it by our one hot vector. We got our embedding for each character. Normally it's matrix E, it's 512 multiplied by our character alphabet, which is 70. So here we're gonna see how tachotron, how our model learns step by step or iteration by iteration, learns this internal representation, the character embedding. We're gonna see like here we use the TensorBoard feature embedding visualizer. And we see the iteration. When the iteration is going on, we see the clusters, like plosive characters are joined, like D and B. They have the same intonation, D, B, and U, O, all the vowels, and the W have formed also their clustering. We have here the special characters that are used to stop, and that are mostly linked to a silence in the waveform. So this is the main important thing in the text to speech. You should have your characters, embed them, and create these clusters to try for the synthesize, to have a better synthesize for each character. So this is so after training our model tachotron, we get this alignment, which is a correlation between the encoder. We have here the time dependency. We get our waveform. Here we use it as a vocoder. We use the graphineline. And we see we get the alignment after like 10,000 iteration, which is take especially one iteration takes more than 30 minutes. So it was after 1 week we start getting our first alignment to map the text to a wave to a spectrogram, and from spectrogram to a waveform. Can you hear the voice? This is the original wave.
No, we hear nothing.
No.
Sorry. Sorry, there is no voice. So I'm gonna send you the samples. It's better to. I'm gonna share the slide for listening to the samples. So I'm gonna just pass. And this is one way we created to evaluate our model in the training. We tried to see the time, the predicted time versus the original time of our predicted waveform. And on all the data sets, we plot this, and we see if they are. Normally, we cannot have. Like the first bisectrice, all the elements in the first bisectrice, but we had the cluster. It's very encouraging results, because we didn't have any errors in the prediction. And I have here also some examples to see that Tachotron was able to get the context of the sentence, and it was resilient to spelling errors. And he gets he thought it was time to present the present, and there are two words, and he gets that one is a noun and one is verb, and all these tongue twisters, this all difficult sentences to pronounce. He was so resilient to pronounce. So I'm going to share it with you. And for the paper, we get likely the same result. It was like very realistic sounding tachotron. So just the result. So we want to say if text-to-speech are solved, all the problems in text-to-speech are solved. No. What are the points that we should work on? It's we have the lack of controllability, so we cannot control the prosody, we cannot control the style. We have just one neutral voice. We have not this expressive component to get to try to have some emotional part, some expressive part. We have just no neutral voice until now. So we worked on this. As a conclusion, I want to say that end-to-end speech synthesizers are very promising. They are simple, powerful, and flexible. They give us realistic humanoid voices. They are context-aware text-to-speech, and they are resilient to errors. So in next presentation, we're going to talk more about the data, how we process the data, how we clean the data, how we make it more switchable for text-to-speech synthesis, and also the architecture for more expressive text-to-speech, and the result of our study that we did. And we proved that paralinguistic component could be conducted through end-to-end speech synthesis. So that's all. Thank you very much for this presentation. So if you have some questions or some interventions for about these topics, I'm very glad to share with you my point of view about it. So, hello, do you hear me?
Yeah, we can hear you. First, I'd like to thank you for the presentation because it was very interesting and complete and very go deep in some of the detail and technical detail, and that's very helpful for the people, you know, to go into the technical background. So yeah, do we have some NLP experts that could have some very interesting question to deep dive or to address? Don't be shy. No question? Everything was quite clear? I'm not an NLP expert, so I don't want to cannot help on that. But yeah, but that I found this very interesting. But maybe we could. So I let the mic open for someone. If we don't have any question, you can reach.
Hi, this is Kanu here.
Hello. Oh, sorry.
Yeah. Hi. At present, I don't have any question, but if I have questions later, I can ask in the chat.
Yeah.
Is that okay?
Yeah, you are welcome. Yes.
Of course, the presentation has been recorded, so you can replay it if you want. You can share, comment into the circuit conversation, and we will upload the slide as well. So yeah, don't hesitate to reach Badreddine. And very thank you again. If we have no question today,
hi. Sorry. Yeah.
Yeah, please go. Yeah.
Sorry, I was on mute here, talking to myself. Thank you for the presentation. Really throughout, very technical, really good. I have a question about if I understand correctly, this is part of a project called Teradia RD, which is part of the conversational agent for therapeutic. Can you explain a little more or how it fits in?
Like the character embedding?
No, this is part of how they call it, Teradia.
Yeah, the project is called Teradia. Is a project when we want to build assistance for patients, and like it has the generation of verbal and co-verbal behavior. We should understand the state of emotion of our patient, and we should generate for him relevant information and relevant emotional state for this situation. So for my work is for the generation of verbal and co-verbal behaviors, and there is other company and other lab that work on the understanding of the patient behavior and the patient's emotional state, and it's a big project which Atos is a part of it. There is 2 labs and 3 other companies.
Excuse me, I'm Beatrice Bouchot. I'm working on this project. So if you are interested in this project, we need to have more time to explain it. So perhaps it will be another presentation dedicated to this project. Because
yes, that would be very interesting.
Okay.
I'm working on.
Yes,
it's not a similar project, but it is a virtual care system. And we've been discussing the possible use of virtual assistants to help in the front office. Doctors.
So Thierry asked me to present the project, but I didn't have enough time today to do it. So we will plan it for the next month if you are interested in it.
Yes, definitely. Yeah.
Because it's a very huge project. It's an R&D project for 4 years. We have 3 partners, 3 research laboratories with us, and 3 industrials. So it's a huge project. I need to have more time to explain it. It's for health and cognitive disease problems. So
yeah, that's very interesting. We've been working in the computer vision aspects for doctor-patient, and yeah, maybe we can have a conference of yeah, that's
no
very
problem.
Very nice.
Hello,
thank you.
Badreddine.
Thank you for the presentation. Really, really nice. Yeah.
Hello, Badreddine.
Yes, hello, it's Ricardo.
Okay,
Yeah.
thank you for this presentation. I see this is very interesting. As we are trying to do the same jobs by doing a TTS, our language, our language in Africa. Sometimes we see we have many people don't use don't go to schools. We have a same project, but we use for the first time Tokotron to do this job. But we don't have we don't know how amount of data we need to have a better model of, or if you have many interesting.
Typically, for text-to-speech, you should have like between 20 hours to 30, 40 hours of speech recorded in this language. And also, yes, it will be. I will explain it more on the other. I will do other presentation about just the data, how to arrange the data and all the segmentation of the data. How do you get it? Because we work in open source data, and in open source data there is a lot of errors, of segmentation errors, a lot of noise. Because to have a good text-to-speech system, you should have a really good sound quality system. Noise is very effective to this kind of systems, of text-to-speech systems. So you should use for the pre-processing, you should denoise the data, you should annotate the data, you should have small utterances, like yeah, it's I will also show all the work that was processed just on the data, how it took open source data and make it usable for text-to-speech system.
Okay. So we need further details to do the same things. Perhaps we can get our to collaborate.
Yeah, you should record. It's better to have a studio quality, like a good voice, like Google, what Google Assistant and Siri and all. They use like singers voices, and they record 40, 50. They have hundreds of hours, and they train models on hundreds of hours in a studio quality sounds, with no noise, no ambient noise, no anything. And
Okay.
with the correct, yeah, it's because it affects. And also you should use recent speech data, because in our French we had like some problematics, like in French, like architecture, ch is read sh, but before like 1980, ch was read k. So it's like English architecture. So in our data, we used all data, and all the ch was read like with not sh. So it's yeah, the choosing of the data is very important for text-to-speech.
Okay. Thank you.
That's all. There is any questions?
Okay, then
Yeah.
if we don't have no more question, I suggest to close the session. And if a question comes, you can directly reach Badreddine or put a message into the circuit conversation.
Thank you.
I wish you a very good day. Thanks again, Badreddine. Have a good day and stay safe all, and talk to you in 1 week.
Yeah.
Thank you.
Bye-bye.
Thank you.
Hope to see you in the next presentation. Thank you very much.
Thank you.
Thank you.
Thank you.